Hi everyone. We are starting a new unit, Unit 13, Aromaticity. And aromaticity is a stabilizing force. It makes molecules uh, more stable, but it's different than resonance. And it's different than other ways that a molecule can delocalize electrons. And that's typically how stable molecules become stable. They tend to have a delocalization of their electrons. But aromaticity is a little bit different, and the story about aromaticity starts in 1825 with Michael Faraday, and he was burning benzoin for heat or light. Benzoin is coming from the resin from a tree bark, and he isolated an unusual compound, a compound that had a very atypical carbon to hydrogen ratio. So from the soot, he isolated a compound that had a carbon to hydrogen ratio of 1 to 1. Now, most of the fuels, they knew the molecular formula for natural gases and for low molecular weight um, liquid fuels like propane and butane. Those are all alkanes. And you know that the alkanes have a general formula of CnH2n plus 2. So you notice that this doesn't fit that formula. Okay, so there's this unusual molecule with a carbon to hydrogen ratio of 1 to 1. Now, as students of organic chemistry and us knowing, the bonding rules of carbon, this might be very easy to figure out. This is benzene. Benzene ultimately, who was it? Ultimately, Kekule proposed this structure. Okay. Now, when you look up benzene on the internet, sometimes they'll draw it like this with a circle in the middle. Um, I it's preference, but I don't like drawing it this way because there's some molecules that have fused benzene rings, and it's hard to tell how many double bonds you have when you represent the benzene ring like this, right? Just let me just give you one example of why I don't like using a circle representation. We'll discuss though why this is common, but not just yet. And let's see, what can we do like this? All right, so that's what is that? That's naphthalene, and sometimes you'll see naphthalene drawn like this. Okay, but again, how many double bonds does that have, right? For benzene, that circle represents 3 double bonds. For naphthalene, it represents 1, 2, 3, 4, 5 double bonds. Okay, 5 double bonds total. So just stick with the line structure. And anyway, we know that benzene is this, okay, and it does have a 1-to-1 ratio, but back in the early 1800s, these were some other proposed structures for a molecule that has a formula of C6H6. Okay. And if you follow your rules for um, tetravalent carbons, you'll notice that all of these do have 6 hydrogens. Okay. I especially like this one, prismane. Okay, that's a pretty symmetrical looking structure. But ultimately, benzene was discovered to have this formula, and or that not only this formula but this structure. So this was proposed in 1866 by Kekule. Give me 1 second. Okay, but the thing is, e even if you use your models, you recall that double bonds are shorter than single bonds. And so really what Kekulé was thinking is that you have a double bond that's shorter, single bond, double bond, single bond. Okay, not great in terms of to scale, but I tried to make all the double bonds shorter than the single bonds. And it was known at the time that the length of these bonds, a typical carbon-carbon double bond, was 1 point short, right? 1.3 angstroms, and the single bond is 1.5 angstroms. Okay. And don't forget, an angstrom is how many meters? 1 angstrom equals 1 times 10 to the minus, if it was minus 9, it would be a nanometer, but it's minus 10, so that's an angstrom. Okay. But about, 50 years later, even more than 50 years later, 1928, Pauling proposed that these electrons are delocalized. And we've done this in the past. We've drawn mechanism errors to show resonance structures. So benzene has a resonance structure, or does undergo resonance to form the structure here. Yeah. So look at the timetable. It took 100 years, right, to go from discovering this unique molecule with a 1-to-1 ratio to a line structure, although without the use of resonance, they believed that benzene had these bond lengths, to 1928, where Pauling said that these pi bonds are delocalized. Pi bonds, delocalized. I know it's a long story. We haven't got anywhere near resonance just yet. We are talking about resonance, though, and you know that resonance is a stabilizing effect. Now, what is some experimental evidence that this actually occurs? Okay. We'll talk about the stabilizing effect in just a bit, but the evidence for this movement of electrons comes from the fact that every carbon-carbon bond, whether you draw it as a single or double, in real life, it's 1.4 angstroms. 1.4 angstroms. So it's totally identical, every carbon-carbon bond. Now we know from past discussions that the resonance hybrid is this, 1.5 bonds for each carbon-carbon bond, right? If you isolate any two carbons, let's take the two on the right, we have a double bond for one resonance structure and a single bond for the other. The average is 1.5, and you could indicate a partial bond, in this case a half bond, by a dotted line. And that's where the idea of drawing benzene as a hexagon with a circle in it came from. Okay, so these are dotted straight lines. Okay, but what this means is that, or trying to indicate, is that the electrons are whizzing around. It's going to be very essential that we learn how to count pi electrons, because that's going to be one of the uh, determinants of whether our molecule is aromatic or not. Okay, so this has 6, right? You're just looking at all the electrons that make up the pi bonds. So several times I mentioned the word aromatic or aromaticity. That is maybe a misnomer, because this first isolated compound, benzene, had a smell to it. Benzene and its derivatives have some people can describe it as a sweet smell. Yeah, why don't we just put that? So historically, that's where the name aromatic comes from. But it, now it has come to represent something else. Comes to represent a molecule that has remarkable stability. So it's pretty unreactive unless you have special catalysts, which we will see in the different units. How do we react these uh, aromatic molecules? So a molecule that has remarkable stability. Um, yeah. So due to this idea of aromaticity, not right in parentheses, not due to resonance. Now, aromatic molecules undergo resonance. They show resonance, but there's an added kicker of stability due to this right now nebulous term called aromaticity. Okay. Um, so before I go over the rules of aromaticity and how to determine whether a molecule is aromatic or not, let me just take care of I think two more things. The first thing is this idea that benzene can have resonance. Is that really true? Now, we, one piece of evidence is that the bonds average out to each be 1.4 angstroms. So that indicates that all carbon-carbon bonds are 1.5 bonds. Okay. Another evidence that it is true is that if you mark two of the carbons by putting chlorines on them, and you show the resonance structures for these two molecules. Okay, these two molecules. And the chlorines are here. Now we can really tell that between the two chlorines, the carbons connected to two chlorines, one of them is a single bond and one of them is a double bond. So it's not a question of whether, we're rotating the molecule to get this one. We're really getting this second molecule by shifting or delocalizing the pi electrons. It's not as if these are considered identical structures. They are two resonance contributors of the same structure. Okay, so I know that's a little bit subtle, but I think this will help clarify some things. This is molecule A and molecule B. Now, just by looking at them, they look different, right? We have a single bond here and we have a double bond here. You would know these as constitutional isomers. Constitutional isomers. But because of resonance, these are actually identical. And because they're identical, there is no such thing as being able to isolate A from B. So you cannot have a jar of A, nor can you have a jar of B. What do you have a jar of? You have a jar of the resonance hybrid. The resonance hybrid is, again, this. Now you can see that this is kind of a pain to draw, okay? And that's why chemists say, well, you could represent this molecule via either of the two resonance structures and not worry about it, okay? You don't have to draw the resonance hybrid, even though this is 100%. You really don't have these two molecules. These are just representations, valid representations of the actual hybrid molecule. Okay, so that's part one, or the one of the points that I want to get to before we actually get to the what? Before we get to the rules to determine aromaticity. Number two is this. Experimentally, is it stabilized? Okay. And we're going to compare a couple of molecules. We're going to compare benzene versus cyclobutadiene. Okay. Cyclobutadiene. So there are a couple of things. If I react this with Br2, experimentally I get no reaction with benzene. But if I take cyclobutadiene and I react it with Br2, and we'll say just one equivalent, we get this. Okay. As gotta be careful about this. Yeah, we get this as the major product. As the major product. So that, what does that imply? That implies that benzene is more stable than cyclobutadiene. Okay. I'm comparing these two because, well, every carbon is sp2 hybridized. Okay, and on paper, yeah, on paper, we could draw mechanism arrows to show resonance. So one last time, resonance for benzene is this. Okay. But for cyclobutadiene, okay, theoretically you should be able to do this movement of electrons to get a second resonance structure. This one right here. Okay. But in actuality, while this one does undergo resonance, it was shown that cyclobutadiene does not. So we'll put X here. Okay. No resonance. No stabilization. And stabilization due to right now resonance. Okay. But we're going to see later that it's more than resonance. It's this term called aromaticity. Okay. And the last piece of evidence is yes, when you do measure the bonds of these two cyclic molecules, again, both of these bonds are 1.4 angstroms. Okay. But this one maintains its common carbon-carbon double bond length and its common carbon-carbon single bond length, 1.5 angstroms. Again, it doesn't imply now, or it's implying that you cannot do resonance with this molecule here, which is unusual because I can see on paper that I can move those electrons. Okay, there are other molecules that have this sort of double bond, single bond, double bond alternating pattern where you cannot do resonance. This is one of them. Okay, another one of them is the stop sign. Okay, and if we have double bond, double bond, double bond, single bond alternating, yeah, on paper we should be able to do exactly what benzene does and rotate all the double bonds around the ring. But again, this has no resonance. Okay. All right. So that is a little thing about stability. Stability. Let me go over here the rules to determine aromaticity. It's going to take a lot of practice, though. We're going to have to see a lot of examples because there are going to be some tricky molecules that seem to obey the rules but actually don't. In this video, let me give you the rules, and then in subsequent or following videos, we're going to look at as many exceptions and examples as possible, okay, in a reasonable amount of time. Okay, so the 1st rule for aromaticity. shoot. The first rule is 1. All atoms that make up the ring have to be sp2. Now, atoms that are coming off of the ring don't have to be sp2. All ring atoms are sp2. You know why that is, correct? Because now every atom has a p orbital, and we saw in a previous unit, conjugated dienes and polyenes, that if you have sp2, a line of sp2 carbons, those pi electrons can travel up and down the molecule. Okay. So that's a type of delocalization, okay? But that's not aromaticity, okay? Number 2, the molecule's flat. To have these p orbitals that are on the sp2 atoms aligned, right, the molecule has to be flat. And then that way we'll get good alignment of the p orbitals that allow the electrons, the pi electrons, to, again, be delocalized. So it has to be flat. Number 3 is a key rule, and this is going to help us separate the difference between resonance stabilization and aromaticity stabilization. And that is, we have a scientist, Huckel, and he came up with a formula to figure out whether you have the right number of pi electrons, because you need to have a Huckel number of pi electrons. What are those numbers? 2, 6, 10, 14, etc. So you start with 2 and you increase by 4. So the formula that you see in the textbook would be, what would it be? It would be 2, oh, 4n plus 2. So if n equals 0, that's 2. If n equals 1, that's 6. If n equals 2, that's 10. This n doesn't mean anything. It's just a trick to help you memorize, or a formula to help you memorize the actual numbers. Okay, so I don't typically like Huckel's rule. Huckel's rule says you have to have 4n plus 2 pi electrons. I would just rather know that you start with 2 and you add 4 each time. Okay. So if you follow all 3 of these rules, that molecule is aromatic. And so benzene is an example. You have 6 pi electrons. Okay, it is definitely flat, and every atom on the ring is sp2. Your conclusion here is that this is aromatic. We have not yet gotten down to the meat of what it means to be aromatic. This is just requisites or prerequisites to, or requirements to know that a molecule is aromatic. Okay, but I haven't explained why there's more stability here than what you would normally expect from resonance. Um, okay, what about this molecule here? Okay, we saw that that had very different properties than benzene, and it did not have this added stabilization. Well, that rule is this. If you follow rule 1 and 2, okay, all ring atoms are sp2, the molecule is flat, but not 3. You are what's called anti-aromatic. Anti-aromatic. Okay? And there's one last thing. if any molecule can be categorized as aromatic, anti-aromatic, but there's one last piece. If not aromatic or anti-aromatic, you default into what's called non-aromatic. So look at my three terms. Again, this is not going to sink in until we see many, many examples. Okay, and don't worry, in the next 1 or 2 videos, we're going to see many examples. But those are your three categories. Look at my rules. How do you become non-aromatic? A great way to become non-aromatic is that the molecule is not flat. You don't follow rule number 2. Okay, or you have an atom that is not sp2 hybridized. So for instance, well, I'm not going to show you examples just yet. Okay, we'll go over examples in the next video trying to apply these rules, but let me give you one last tidbit. If your molecule is aromatic and you follow all 3 rules, you are very stable. If you're anti-aromatic, not only are you not stable, you are actually unstable. I'm going to say not very unstable, but surprisingly unstable. Maybe another way I could say it. Unstable and reactive. That's another way to write unstable. You're very reactive. Non-aromatic means you're agnostic. You're neither very stable, like aromaticity has nothing to do with it, with the stability of that molecule. So you are, I don't know, has nothing to do with aromaticity. The molecule has nothing to do with aromaticity. Either aromaticity or anti-aromaticity. Okay. Next video. Again, I didn't explain what's behind the curtain. Why it is why do these rules add extra stability? Or specifically, why does Huckel number of pi electrons have or confer added stability? Okay. And that added stability is called aromaticity. And I know I've said this many, many times in this video, aromaticity is not resonance. Just because a molecule has resonance doesn't mean it's aromatic. And the stability that we see with benzene is not due all to resonance. Maybe that's the take-home lesson. Stability of benzene is not due just to resonance. Okay? Big star. And we will explain that in the next video. It's going to get a little bit weird. We're going to look at what's called molecular orbitals and the different energy levels of those orbitals. All right, I'm okay with that introduction to aromaticity and aromatic molecules, and we do have a set of working rules that we could work with to determine these 3 categories, molecules that fit in these 3 categories.